These are the Chapter 8 Notes 3 on means and standard deviations of binomial distributions. We're going to start with a problem today, and I'm just going to read this aloud. It says, orthodontists estimate that 45% of children need braces to fix functional problems like a misaligned bite. Let's assume that this percentage is what a newspaper writer uses to estimate the percentage of teenagers who are wearing or have worn braces. The reporter hopes to interview 3 teenagers who have worn or are currently wearing braces about a story regarding personal image. The reporter starts by quickly asking the first 10 teenagers seen outside the newspaper office if they have braces or are currently wearing braces. In problem 1, you're asked to describe the distribution of 10 teenagers, assuming 45% of all teenagers have worn or are currently wearing braces. Now, usually when it says describe the distribution, we're kind of thinking socks, shape, outlier, center, and spread. However, this distribution is kind of special because it does sound like it meets the 4 components of a binomial distribution. Now, you might remember the 4 components. Binomial means 2, so there's 2 outcomes, success or failure. So either a person is wearing braces or they aren't. Second option we're looking for is independent trials. It doesn't say that here, so we're kind of assuming independence in this case. But I think that's reasonable based on just asking 10 teenagers, kind of assuming maybe they're not related. Same probability of success for each trial. It does say we're supposed to assume 45% of all teenagers have worn or are currently wearing braces. So every person we talk to, there's basically a 45% chance. And then a fixed number of trials. We are asking 10 teenagers. So we're hoping to get 3, but we are going to ask 10 teenagers. So we might get more than 3, we might get less than 3, but there are a fixed number of trials. This is a binomial setting. And if you have a binomial setting, instead of having to go through the SOX rigmarole, what you are allowed to do is you're allowed to say this. You're allowed to say that this is a binomial distribution. We're going to abbreviate that with a capital B. That kind of gets at what the shape is. Then in parentheses, what we're going to put is we're going to put the fixed number of trials, which is n, in this case it's 10, followed by the probability of success, 0.45. If you ever have a binomial distribution, you can describe it this way instead of having to say shape, outlier, center, and spread. Eventually, you'll get to understand what this kind of means as a graph, but for right now, this is a valid way of describing the distribution. Capital B for binomial. Remember, we used capital N for normal earlier. Then you put the number of trials and the probability of success. So while problem number 1 is kind of new and unique, the rest of the problems here should sound kind of familiar. For example, in problem 2, when you're finding a probability that less than 3 teenagers surveyed have worn or are wearing braces, you might be thinking less than 3 means we're counting down from something. Count down from CDF. Maybe there's a way we can use a CDF formula here. In problem 3, we're supposed to use a formula from the formula sheet. And you might remember that when you're calculating multiple probabilities, we're going to have to go through that formula that involves our parentheses, the probability of success to a power, the probability of failure to a power, and we might be adding several of these together. Problem 4 is looking for the probability distribution for x. So this is looking for individual single probabilities. You might want to think of these as being like PDFs. Probabilities for 0, 1, 2, 3, or 4 kids wearing braces. So you're going to have to run through the PDF formula several times, but there is a calculator shortcut that we talked about last week that you can use as well. Once you have a table set up here, we can use one var stats to find the mean and the standard deviation of these probability distributions. Go ahead and do that, and then we'll come back in a little bit and we're going to talk about the back side of your worksheet and some shortcuts that you can use for finding these means and standard deviations. All right, so we calculate some values on the front side of our worksheet for things like the mean and the standard deviation, and we did that by utilizing some features that we used in earlier units where we calculate probability distributions. You can multiply each x times its probability, add them together. We had a big formula for standard deviation you can use. One var stats gets you the information a little bit more quickly. However, there's even a faster method, and for this we're going to utilize our formula sheet again. And on your formula sheet, it talks about this thing called binomial distribution, and it happens to give a formula for the mean and the standard deviation as well. So if you have your yellow formula sheets, you can refer to that. I'm just going to write down the formula for the mean. The mean of a binomial distribution can always be found by multiplying n times p together. And the formula for the standard deviation, which is also on your formula sheet, is the square root of n times p times 1 minus p. Now, if we know the standard deviation, we can square this to get the variance. And if you square a square root, the square and the square root cancel each other out. So the variance is just n times p times 1 minus p. So if we use these formulas to find the mean and standard deviation of the binomial distribution described in problem 1, in problem 1 you might recall that the n value was 10 and the probability was 0.5. We can just plug in 10 and 0.5 in for n and p. And if you multiply 10 times 0.45 together, you get, well, 4.5. You just slide the decimal place over. Standard deviation, we're going to take n times p, which we actually just did. But then we're going to multiply this times 1 minus p. Now, if you know what that's equal to, you can write 0.55 there. If you'd rather just do 1 minus 0.5 here, you can do that. So on the calculator, again, pretty straightforward. We square root this, 10 times 0.45 times 0.55. And the answer we get should sound kind of familiar because it's the same answer that we got on the front side of your worksheet. It's that 1.57 number. And you might recall back on problem 6, we got the 1.573 there as well. So things check out. This is a whole lot easier than having to go through every single value on this chart that's possible and go through this process of finding means and standard deviations. This method will always work, but if you have a binomial distribution, you have a nice little shortcut that you can use. So let's talk about the shape of the binomial distribution. We kind of ignored the shape earlier when we talked about describing the distribution going this model, but what shape is it if you're actually interested in knowing what the shape was? A couple ways of figuring it out. Option 1 is to take our table here and graph these values. Now, I noticed that I didn't use a very good scale here. Our probabilities don't go any higher than about 23%. So I'm going to change these values just to make the graph look a little bit nicer to 0.05, 0.10, 0.15, 0.20, and 0.25. None of the probabilities exceed 0.25, so I just think that kind of makes sense to go that route. So what we can do is we can graph these one at a time, and our probabilities start at about, well, 0. And then they start to rise to 7, 16, 23, 23%. It's about our high, and then it kind of goes back down 15, 7 to 0.5%. You know, this is almost 0. So let's graph these values and see what this looks like. So here we are at the halfway point. This is the value that corresponds with a probability of 4. On the front side of our worksheet, we calculated that to be about 0.238. So that's what I've graphed here. This value corresponds with 0.238. Then the next value on the chart is 0.234, which is very close to it. And then the probabilities will continue on their way down. So here's what our probability distribution looks like. And if you were to describe this shape, you know, it's sort of bell curved. It does kind of meet that approximately normal look to it. It's certainly going to be, I think, approximately symmetric. Just by first glance. I think the other thing that you could possibly say is, here's your 2 tallest bars here, and you kind of go, okay, here's the next 2 tallest bars, the next 2, the next 2, the next 2. There's a slightly longer tail on the right side, so I think you could also make an argument that this graph is right skewed. I would stay away from saying it's bimodal despite the fact that there are 2 tall bars, because usually if the 2 tallest bars are in the middle, we'll typically say something like normal or symmetric. Usually you want to say something like bimodal if there's kind of a space in between the 2 bars. So based on this graph, I think you could kind of go with these. Now, Officially, there's a formula that you can use to verify if a graph is normal or not. So if you're like, is this graph normal? Officially, a binomial distribution can be considered approximately normal if the following two formulas are true. If n times p is greater than or equal to 10, and if n times 1 minus p is greater than or equal to 10. So officially, is this graph approximately normal? Let's find out. In our problem, we've already calculated n times p. That was our mean. 10 times 0.45 was 4.5. And if we're comparing this versus the number 10, 4.5 is definitely not greater than or equal to 10. So we're going to draw a line through that. Officially, we'd also would check to see if 10 or n times 1 minus 0.45 would also work. And if you do 10 times 1 minus 0.45, you'll find that we get kind of the same kind of answer here. What we get is 5.5, and that's also not greater than or equal to 10. Both of these formulas have to be true in order for this graph to be approximately normal. So officially, this graph is not approximately normal. But why not, Mr. Herrick? It kind of looks approximately normal. I guess here's a couple of things I think are going on here. I think one is dealing with the idea that this graph might be slightly right skewed. Now, these numbers aren't really close to 10, so I think something else is going on here as well. And I think part of the issue we have going on here is if you imagine a normal curve. So if you imagine putting a tarp like on top of this. Typically on a normal curve, you see kind of this graph kind of spreads out and heads out kind of this way for a little bit longer than what you see here. This binomial distribution stops. It stops at 0 and it stops at 10. And an approximately normal graph will go on forever and ever and ever, but I think what you'll typically see is a little bit more of a tail extending on here. And because these graphs officially stop at 0 and 10, it cuts your approximately normal graph off. So this graph has the beginnings of an approximately normal graph, but because it's cut off so quickly, it's officially not approximately normal. What would you call it? I guess it's kind of symmetric. It's kind of right skewed. If you had to pick one, I'd probably pick one of these two options here.